We have another example on the board. Again, we have two diodes connected parallel. But what's the difference? Please notice that one arrowhead is pointing down and one arrowhead, germanium arrowhead, is pointing up. So let's take a look at the polarity of the voltage source. I have positive terminal over here and negative terminal over here, and the current theoretically must flow in this way because I'm using the conventional current flow. So this is my I total, and I total is going to go through the resistor. So I'm going to have positive sign over here and negative sign over here. And please notice that the current has exactly the same direction like the arrowhead of the silicon diode is showing me, okay? So this diode, silicon diode, is going to be in the on state. It's going to be forward biased, okay? Why? Because this direction is matching to direction of my arrowhead, and this voltage is much greater than 0.7 volts. So this diode is going to work. If you are going to look at this one, the current will want to go through this diode, but this diode is opposing the direction of the arrowhead, right? Is opposing the direction of my current. So this diode is going to be in the off state. So this diode is not working. It's behaving like an open circuit, okay? So the current is not going to see this diode. So we have simple series circuit, okay? Again, we have current going through the anode and leaving at the cathode. So I have positive sign and negative sign. So if someone is going to ask you what is the output voltage, how much is the output voltage in this circuit, you're supposed to realize that output voltage is the voltage between output terminal and ground. So this is the voltage across the silicon diode. Okay, and the voltage at the silicon diode, when the silicon diode is conducting, is equal 0.7 volts. This is the transition voltage. Okay, so I can write that V out is equal V silicon, and this is equal 0.7 volts. Next, we're supposed to find the voltage across the resistor. So if you want to find the voltage across the resistor, you're supposed to write the KVL equation. Why KVL equation? Because we want to practice it. Okay, so I'm going to start again from the ground. So I have over here negative voltage source plus voltage across the resistor, and I have plus voltage at the silicon diode, and everything is equal to 0 volts. If you are going to solve this equation for VR, because we're looking for VR, so VR is equal voltage source minus V silicon. This is equal 9 volts minus 0.7 volts. This is equal 8.3 volts. Okay, so this is the voltage across the resistor. Next, the problem is asking me for the current which goes through the circuit. Okay, so I total. I total, in our case, is equal to the current which goes through the silicon diode. Okay, and this is also the current which goes through the resistor. Why? Because we are talking about the series circuit. We said this diode is not seen by current, so I have series circuit. In series circuit, we have the same current. So I have IR is equal VR over resistance, where VR is equal 8.3 volts over the resistance 3.3 kilohms. Everything is equal 2.51 milliamps. Okay, so this is the current in my circuit. Next, if you want to find the current which goes through the germanium diode, we said the current is not seeing that, so IGE is equal 0 amps. Next, we're supposed to find the maximum forward power dissipation at the silicon diode. So I have P silicon is equal the current which goes through the silicon diode times the voltage of the silicon diode, transition voltage. Okay, so I have I silicon is equal 2.51 milliamps times 0.7 volts. Everything is equal 1.75 milliwatts. Okay, so this is the power at the silicon diode. Next, we're supposed to find the power at germanium diode. P GE is equal I GE times VGE. Please notice that IGE is equal to 0 amps times 0.3 volts. 0 times anything gives me 0, so that's why I'm going to write this as equal to 0 watts. Okay, next I'm supposed to find total power. P total is equal I total times voltage source. I total we found is equal 2.51 milliamps times the total voltage, which is equal 9 volts. Everything is equal 22.6 milliwatts. Okay, so as you can see, the problem is solved.